Hello students, in this lecture we'll be doing some numerical problems based on the previous concepts we have studied. In order to grasp the concepts, let's try some examples, and then after that we'll be starting with the next topic. Okay, so here are some questions. So the first question says, a cloud that is about to unleash a lightning bolt that has a charge of plus 24 coulomb. If cloud started out electrically neutral, how many electrons were removed from it to give it this positive charge? So the question says that we have the situation where the cloud that is about to unleash a lightning discharge. So what is this word meaning? Unleash means that there is sudden release of we can say, in this case, sudden release of lightning bolt, and now that cloud has a charge of 24 coulomb. So it was initially electrically neutral, and now it has 24 coulomb charge. So we can say that if it has plus 24 coulomb charge, so the charge developed on the cloud is plus 24 coulomb. That means the total charge of electrons removed is minus 24 coulomb, right? So this much amount of charge is removed from that cloud, and now we have to tell how many electrons were removed. If minus 24 coulomb charge is removed, then what is the number of electrons that are removed to give it this positive charge? So now in the first lecture, we have seen the properties of the charge, and one of the properties of the charge was quantization of charge, which says that Q is equal to NE. So this is the property of quantization of charges. Okay, quantization property, right? So here we'll be putting that we have the charge 24, and of course minus 24 is removed. So let's keep it here magnitude, or if we want we can solve it with sign also. So if we have minus 24 coulomb here, so n we have to find, and we know that the we have the sign of electrons minus because they are negatively charged. So again they will be cancel out here. Now we can calculate the number of electrons, and the value of the electrons number can be calculated by keeping it on the left. So n equals to 24, and charge on one electron is 1.6 into 10 raised to power minus 19 coulomb. Okay, on solving we'll be getting the answer 1.5 into 10 raised to power 20. So these are the number of electrons which will be removed in order to have the charge of plus 24 coulomb on the cloud. So this was the strategy, or we can say that concept for solving the question. Okay, so now let's proceed to the next problem. In this question what we are given is, so we are having two particles having the mass m and charge q are placed on the rough horizontal surface with coefficient of static friction mu. So we have a system of two charges, and they are placed on the rough horizontal surface. What can be the minimum separation between them so that they remain stationary? So let's understand the question first and draw the situation, and then we'll see what we need to find. So basic thing is, in order to solve the questions of the physics, first you understand the whole situation, whatever is happening over there, and most of the times you are given very much clues in the question, and you can proceed whatever is given in the question, and you will reach the answer accordingly. So first, since I have been given the situation like this, that we have a rough horizontal floor and we have two charges. So we have two particles, and both the particles have are identical, and they have mass m, they have charge q, and since the charge on both the particles is same, so they will also be experiencing a electrostatic repulsive force, right? And we are also given that they are placed on the rough horizontal floor, so of course they will be uh, facing this static friction also. Okay, so the situation is like this: the both the charges are experiencing this repulsive force, and if they will move, mm, suppose this charge starts moving towards right, so it will be experiencing a friction force against the motion. So friction force will be in this side. Similarly, this mm, particle will be experiencing frictional force on that side. So now the situation is like this, that if we displace a charged particle, suppose I displace this particle from here to here, so it will experiencing a repulsive force due to this, and it will be pulled in this direction. So therefore the situation is like this: we have to find the minimum distance that they are in equilibrium. If I displace that particle from that position to either this side or right side, so it will be displaced. As we are seeing the concept of stable and unstable equilibrium in class 11th, we have seen, right? So the situation is quite similar. We have to find the minimum separation so that the charges remains to be stationary. So if we see that what forces will be balanced in order to keep the charges to be stationary. If I now draw the free body diagram, so we'll be having a clarity of the situation. So if I see that weight is acting downwards on both the bodies, here also mg, and normal reaction is upwards, so I'm drawing normal reaction upwards, and we know that since the vertical forces are balancing each other, that normal reaction is balancing the weight, and mm, so there will be no vertical force in this direction, and in order to keep the horizontal direction also, means horizontal force also zero, so that no horizontal force will act, and our aim is to keep the particles in the stationary state. So if no force will act, so there will be no motion of the particles. So we'll be seeing that in the horizontal direction there are two forces acting on the body, that is electrostatic repulsion force, and this friction force is balanced mm, by this. If it happens, so then our system will be in stationary. Okay, so let's balance these forces. Now F electrostatic is equal to frictional force. So the concept of friction we have studied in class 11th, that for either to find minimum or maximum either force separation, we can use friction force to be the exactly mu n. So we have the expression of electrostatic force of friction, that is electrostatic force of repulsion, that is 1 by 4 pi epsilon naught q square upon r square, and the value of friction is mu n, and we'll be substituting the value of n to be equal to So N is balanced by mg, the vertical forces. Now we'll be substituting it here. Q square upon 4 pi epsilon naught r square is equal to mu mg, right? So now we have to find the minimum separation. Separation means we have to find the minimum distance between the two charges, or we know that we keep it as x or take it to be r, any variable you can take. So let's find the value of r, and that will be equal to r equals to q square upon 4 pi epsilon naught mu mg, the power 1 by 2. So this is the value of distance. That minimum distance should be this much, so that our situation is, and the situation or the system is in stationary state. Okay, so this is the minimum separation or distance. Okay, so this was the concept for solving this question, and let's now proceed to the next question. So this is a bit conceptual question. Let's read the question. The question says, the electric field at point P due to the charged ball is given by this. So we have the situation like this. I said earlier also that first analyze the situation. First see what all you are given it, and try to uh, imagine or make the situation. So we are given here a charged ball, and it is given that electric field at this point P due to this charged ball will be, as we know the expression kq upon r square. R is the distance given between charged ball and the point P. So further the question says to measure electric field at point P, a test charge Q naught is placed at point P. So we keep a Q naught test charge over here and measure the electric force upon the test charge. Check whether this force upon Q naught is equal to this expression or not. It means that indirectly they are asking that force upon Q naught is what? It is electric field, right? And they are asking this electric field is equal to 1 by 4 pi epsilon naught q upon r square. As we know this expression only, this is the general formula of electric field. So they are asking whether this expression is equal to this or not. So we have to check this. Now in the first go, we'll see that this is the expression of electric field. So one may answer that, right, this is equal to this expression, electric field expression is this only. But let's see the conditions and recall the concept of electric field, that it, the source of electric field, what is the source, how the electric fields are produced. So we know that the source of electric field is charges at rest. So the electric field will only be produced when the charges are at rest. So if we suppose put a point test charge at point P, what will happen is this will experience a repulsive force. So although the field due to the test charge will be minutely tending to 0, but there will be a little amount of force that will cause the ball to move towards back due to electrostatic repulsion. Though the force is less, but there will be a slight movement of the charge, which will cause the charge to be not at rest position. So if the charges is not at rest position and the distance increases, so we'll not have this electric field expression. So our expression will not hold here, and it will not be valid over here. So we can say that it is not equal to this expression, since the distance between the two is increased. So these were the few questions related to the basic concepts, and most importantly we have discussed that questions related to discrete charges, and now we'll be discussing questions related to continuous charged bodies in our next video. So till then, keep learning and thinking.